In this video, we're going to talk about how to plot the kinematics of bump steer using Fusion 360. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to answer a question that came in on the kinematics car suspension that we talked about in a previous video. Now, before you get too excited, there's not an easy way to do this in Fusion 360. What we're going to be talking about is the bump steer in this case, which you can also use this process for things like camber gain and other suspension geometry. But what we're going to be doing is looking at how the wheel turns when the suspension travels. Now, there are a few things that we need to understand about this process. The first is that we need to lock down some of the kinematics to make this work. We don't want the steering wheel to turn because when we're talking about bump steer, typically we're talking about what happens as the suspension travels, but the steering wheel doesn't turn. Now, there are, of course, nuances to this if you're talking about going straight or if you're talking about turning. Now, it's a complicated process because when you turn to the left versus turn to the right, the tires are going to turn more or less based on suspension geometry. We're not going to get down into that level. We're going to talk about some of the basics looking at just bump steer in this example. Now, I think it's important to also note that this suspension was really not set up for a very specific situation. It was just thrown together to show an example of how it could be done. So I am going to guess that the bump steer of this, and I haven't done this yet, but I'm going to guess the bump steer of this is going to be less than ideal based on where the steering rack is. So this position right here, it is trailing the direction of travel, so it's behind the wheel, which in most cases is okay, but the orientation of this, if we look at it from the left, you can see that it's kind of up here, and that's usually not a good thing for it to be that far up. So what we're going to be doing is we're going to be talking about how to set this up and what we can and cannot do with Fusion 360. So if you want to follow along, you can go to the description of the video and download this data set. Again, this was the one we used in a previous video talking about suspension kinematics and how to sort of set all this up without having to have solid geometry. So we were sort of cheating the system by using sketches and components and setting up our joints and the assembly motion in that way. But now let's talk about a few important criteria here. One is going to be understanding how we can lock down joints or degrees of freedom. Two is understanding our measurement process. And then three is going to be what we do with that data. There is no way to directly plot this data in Fusion 360. Now, if you've seen things like the motion study before, that might look like a promising solution, but it's not, unfortunately, because what we do here is we select a joint and then we animate it through a certain amount. Now, in this case, if we say at this point we want to go 5 degrees, then what ends up happening is it rotates the wheel 5 degrees as it travels through that. And if we just loop through this, you can see that it'll just sort of stay there and go back and forth. So that's not really giving us anything to plot the suspension travel. So the first thing that I want to do, because of the way that this was set up, I'm going to take this joint here, which is Rev 9. I'm going to right click and I'm going to lock it. Now when we lock it, it's hard to see, but there's a little lock icon that shows up here. What this means is that the steering can no longer move. And as we move the suspension up and down, you can kind of see what we get with bump steer. And there are some areas where it sort of gets into a situation where it's kinematically unable to solve it, right? So obviously you're not going to have a car with suspension that travels that much. If you have a truck or some sort of off-road vehicle, then obviously you're going to have longer suspension arms and much different suspension geometry. We're not talking about that much travel here. Now, another important thing to note, as soon as we revert the position, that is going to unlock the joint. It's only temporary, and when we revert the position, it goes back. So that's the first step to this process, is understanding how to lock down those degrees of freedom. The second step is the measurement part. Now, this is where it gets a little bit tricky. We have to think about where our origin is and how we want to measure things. So when we're talking about bump steer, typically we'd be talking about the vertical travel of the wheel. This can be measured if you've got a shock or a strut or something inside of your assembly. You can drive the distance of that specific thing. So that's one way that you can do it. Another way is to measure the distance the wheel travels or a point on the wheel travels from the ground. Now, in order to do this, I think it's best for us to measure the angle off of a flat face and to measure the vertical distance off of a point. And there's a reason I'm going to talk about that in just a second. So first, let's think about measuring the angle. Now, when we think about the angle, what I'm going to do is I'm going to take this plane, and I don't really need to do this, but I'm going to make an offset plane just to make it easier for me to see. And then that offset plane is going to be inside of this construction folder. So this construction folder is plane 2. This is going to be my bump steer plane. So this is going to allow me to measure the angle between this and some flat face on our design. So if we go to inspect and measure, and we measure this and this, what we should see is 0 degrees. Now, because this is a kinematic assembly, there's probably been a capture position at some point. We can see that it's 0.61 degrees, and we don't really know what direction that is. Now, if we take a look at this vertically, we can kind of see that it's actually pointing out. So this is toe out. Not a very good situation if you're driving down the highway. That's going to mean that the wheels want to go away from each other. They're toeing out. Again, the suspension was not set up with any of that in mind, so I'm not too worried about that. But really what we need to understand is that base value. Now, in order to track all of this, we're just going to be putting it into a spreadsheet now. So very unfortunate, that's going to be how we're going to have to do it. So the steering angle right now, I'm going to say 0.61 degrees, and the wheel travel is 0. So I'm going to be tracking it on here, measuring different points, and that's how we're going to do it. So the first thing that was important is we understand that base measurement, that base setting. Now, if you're using other programs, things like SolidWorks or Inventor, there are different ways to do this. We're just talking about Fusion 360. Most mechanical design software will have some sort of kinematic tracking where you can plot points as assemblies are moving through their motion. Not really available in Fusion. So again, this is just Fusion. We're not talking about any other software here. The second thing of this is we need to figure out the ground plane. And again, the origin doesn't really give us the ground plane, and it's not required. All we're really looking at is a relative height difference. So all we need to do is we need to make potentially an offset plane, and we can set this relative to the tire. So for example, if there's a point on the tire where you think that is going to be 0, then we can set it there. That's pretty close. One thing that we need to make sure we understand, when this moves, we want to make sure that that plane doesn't move. Now, if we capture position, think about this in the context of the timeline, that capture position would happen after the plane was created. So as long as that's true, that plane should always stick where we put it. And I'm going to call this one my ground plane. So as we're looking at everything that we have right now, we've got our plane to measure our bump steer, and we've got our ground plane to measure the vertical travel. Now, there's one more thing that I want to do here. And the reason I want to do this is because measuring point to point is going to be very advantageous to us. So for example, if we go to inspect and I measure from our ground plane up to a point on our spindle. And so let's just go ahead and grab this. You'll notice that we don't really have any options to see if this is just the shortest distance. We can see the center position in XYZ, but sometimes this can be a little bit difficult to visualize. So what I want to do instead is I want to make sure that I do go to a point. And when I go to a point, you can see that the XYZ position relative to the point, and you can see that we have a distance here. Now this distance is going straight down to the plane. If you want to track other aspects of this. So for example, if you want to see how the wheel is moving forward or backward based on your caster, your camber, and your bump steer, then what you would want to do is you would want to take this ground plane sketch. I'm going to go ahead and create a new sketch on it, and I'm going to create just a sketch point. So the sketch point, it's going to be very difficult to see because the wheel's in the way. I'm going to go ahead and hide the wheel assembly. I'm just going to place it at the origin. Now, typically what you would do is you would use the origin point. That origin point is projected down to this plane. Now the reason we can't use the origin point is because the origin point is relative to the original coordinate system. It's up in space in the wheel somewhere, and that's not going to work for us. So what we want to do is we want to use that point, and it's going to be kind of hard to see, but it's right there. We want to use that point when we measure. And the reason we do that is because if we measure point to point, let's say we grab this point here, now we have this XYZ delta. And the XYZ delta will give us the XYZ on the screen, which is a little bit easier to visualize. That only comes up when we're going point to point. If you're doing point to a plane, it's not available. If you do a point to a line or point to an edge or a face, again, it really only works if you have two vertices. If one of them's construction, if one of them is construction in the sense of a point at a vertex, then we can get those results. So keep in mind that there are different ways that we can do this, and you might have different ways that you want to do it. I'm going to go into the wheel assembly, and I want to find where the sketch is. It says it's in the hub mount. It's kind of in the way, so I'm just going to hide all those sketches. Typically, I don't like to hide an entire sketch folder, but that one's kind of just in the way. And the last thing I want to do before we get onto this is I'm going to go ahead and do a point that's centered on a circle, sphere, or torus. And that is going to be my reference point I'm going to measure to. So we're going to go from there to there and get those XYZ deltas. All right, with all of that done, now we've got our references to measure. And again, I mentioned early on that this is not an easy process. There's no way to quickly automate this that I know of. If there is a way and you know of it, please let me know. So again, we're going to go to that steering joint, which is going to be Rev 9. We're going to lock it. Remember, locking it is only going to work when we don't capture the position. As soon as we capture or revert the position, it's going to unlock that. And then we want to move the wheel up. Now we can already see that this lower arm is angled up. So that means that as it sweeps through its travel, it's going to pull the bottom of the wheel in. So as we go up, we can already see that the wheel is turning. So what I want to do now that I've moved it a little bit is I'm going to inspect and measure. I'm going to go from that point to the point we created on the wheel. And you can see one issue that happens here. That point is not moving with our geometry. So instead of moving with our geometry, it's kind of sitting still at that point. Now, this is a problem that we have when we create construction geometry. And we do that instead of using things like a sketch. So the point in the sketch hasn't moved because it's based here in the timeline. But for whatever reason, until we capture that position, that point is sort of frozen in space. So what we're going to do is go back to our wheel assembly. And because this object is moving, I'm going to go back to the hub mount. I'm going to turn my sketches back on, and that'll give me just a reference point that I can use for now. So I'm going to just pick this lower point right here, and now we can see what our XYZ delta is. Now this is telling us that the distance is 11.3. Now we really need to understand what the original position was, so let's go ahead and revert this. I should have measured that before. Now we're going to go from our sketch point down here, and we're going to go to this lower point. So now our XYZ delta, you can see here that we've got Y is 0, which is good because that's telling us that our fore and aft, along the length of the car, that is not, they're vertical relative to each other. Our Z position, our delta in Z is 10.5 inches, and our delta in X is 1.26. Now the X I don't really care about, but I am going to track all these numbers. So in my spreadsheet, I'm going to go ahead. So we've got wheel travel, steering angle, and I'm just going to do my X, Y, and Z values. I might not use them, but for whatever reason, I might want to use them later. And I'm going to go ahead and put the distance here as well. So again, it's good to track all this stuff. So X minus 1.264. We've got Y at 0.02, Z at 10.501, the distance 10.577. So again, wheel travel, steering angle, and I'm just going to capture all of that data there. So now that we have that base number, again, we need to make sure that this joint is locked. Every time we revert the position, it's going to unlock, and then we can move it up. Now, the best way for you to really do this is to probably have a shock or some sort of joint that you can drive the height or the angle. Now, we could drive the angle of this lower by doing things like animating the joint or driving the joint. But in this case, I'm just going to manually move it so you get an understanding of what we're doing. So now that we've moved it, we're going to inspect. We're going to find that point, the point that we referenced here. And now we can see that our XYZ values, so our X is going to be minus 1.294, essentially the same. It hasn't changed much. Y, 0.038, and Z is 10.967, with the total being 11.043. So that gives us the height difference, but now we need to look at the angle difference. Now, initially, when we measured this, it was 0.61 degrees, and now we're at 0.267 degrees. So the degrees have actually reduced, which means that at this point in space, we're starting to go back to a toe in a little bit. So what we want to do now is we want to move it up a little bit more and get another data point. So again, we're going to inspect. We're going to find that point in space. We're going to measure to here and just capture those numbers. So x minus 1.367. And I'm not going to do this for a ton of points. Obviously, if you're trying to plot this, you need to set it up in a way that you measure each one incrementally. Our y value 0.069 and our z is 11.704, with the total distance being 11.783. Now we want to make sure that we measure the angle. So again, from here to our plane, we're at 0.305. And again, this suspension wasn't really designed for anything specific. So I'm going to go up a little bit more and get into just a couple more points. We can see here, once again, we got minus 1.522, 0.12, 12, 0.752, and the distance of 12,843. And let's take a look at the angle. I think it's starting to go back the other way just visually. So 0.663 degrees. So that's pretty close to what we started at. So as it went up through the travel up to this point so far, what we've done is we've essentially started to toe in a little bit. So it started to toe in, and now that we're getting to this point in the travel, it appears that it's going to start to toe out. So as we go up a little bit more, again, this suspension geometry really wasn't set up for this much travel or really anything, but let's go ahead and just measure one more point, and then we'll take a look at plotting this. All right, so our x minus 1.78, our y is 0.189, and z is 13.956, giving us a total distance of 1407. Now the angle, of course, is going to be important. Let's take a look at this last angle, and that has jumped quite a bit, 2.269 for that last one. So as we're looking at those values, we have got our XYZ, which again is good information to understand, especially if your lower and upper control arms are offset or your spindles are at an angle, if you've got some camber and some caster built into your suspension, you would want to track how these things are moving. Keep in mind, again, we're talking about the steering locked in a straight position. You could do this exact same thing by turning the wheel or moving the suspension a certain amount, capturing that position and locking it, and then moving it vertically through the travel. It just takes a lot of time to plot these numbers. So now as we're looking at this with our wheel travel, with only 5 results here, we don't really need to worry about getting super specific. So what I want to do is this value is 0. So I'm going to say that was essentially we subtracted 10.5 inches. So this one here is going to be equal this value minus this value. And then we're just going to copy that down. And this essentially gives us the wheel travel. So that first one we measured was 0, but really the z value was 10.5 because we were measuring from the ground all the way up to that point on our suspension. So really all we're looking at is the difference here. So as the wheel moves up, we went up about 1/2 inch, 3/4 of an inch, an inch. So that's actually pretty accurate on my part, but going up there and then almost to 1.25 inches. So we can see that this suspension is really meant for about 1 inch of vertical travel of the wheel, which is not much. Obviously, it's not much. And then we can see once it gets that last 1/4 of an inch or almost 1/4 of an inch, then it really starts to toe out, which is a very bad situation for stability in a vehicle. You want those tires to toe in a little bit. So now that we have this, what can we do in order to take a look at plotting this? Well, you just need to insert a graph, and that really just depends on what kind of your level of your level of comfort with Excel or whatever program you want to use. So with Excel, it kind of depends on what your level of comfort is with sort of plotting this stuff. So what I'm going to do is I'm going to plot wheel travel I'm going to plot my steering angle. Those are going to be important to me, and I don't really care about the rest of the stuff. Those are the two things that I'm really interested in. So if I plot those, I can see as my travel increases that the angle is going from essentially a slightly towed out position. And that could be an overstable situation for something like a drift car, because obviously once you turn the suspension, it's going to change. If it's not really meant to go straight, that might be okay. But you can see that we're towing in a little bit. And as soon as we get to this point in the travel, which was, again, once we got to about 3/4 of an inch, then it starts to begin to tow out again. And once we get all the way to, right here at about 1.25 inches is when things start to go really kind of wonky and they towed out drastically. So that is the basic process that we would use in Fusion 360 to track this kind of data. As I mentioned initially, it's not very easy. It's not very clean. It is possible, though. You can do it. There are some things that you just need to be aware of and mindful of when you're doing this. So again, just a couple of things. You need to understand the kinematics of your assembly. In this case, the steering wheel it turned the rest of the suspension geometry. Then what we wanted to do is we wanted to lock that down. We wanted to make sure that that didn't turn while we were moving the wheel up and down. The next thing to understand is the reference points that we're measuring. So while we can create a point on a face like this, as soon as we move the wheel, that point is staying still. And that's partially because that point was done at the top level. Now you can get around that a little bit if you go in and you activate the wheel, for example. So if we take a look at this hub mount and I activate it, and I come in and go to construct and create a point on a center and do it here. And then I go back to my top level. So because that is in that component, now that point is going to move with the rest of the assembly. So it just kind of comes down to the structure of your assembly. If you've got components and subcomponents and you want to create a reference point on one of those, it's important to note that the components moving have their own coordinate system. Everything that's done relative to an active component, the construction planes, the axes, all that stuff, when that component moves, all of those things are sort of attached to it. If you make it at the top level of your design, like we did with these construction planes and that original point, those aren't going to move with the rest of the suspension because they're kind of attached to the top level coordinate system. They're referencing this and they're not going to move when the component moves. So there are those nuances that you need to be careful of when you're doing something like this. Again, if you have sketch points, those are perfectly fine. All we're really looking at is the delta or the difference between the starting and the end point. So as long as you have 2 points that you can track, doesn't really matter what those values are because it's a difference that we're looking at. And the last thing is just sort of brute force, all right? So this design would have been better had I had a shock setup where I could alter the distance, the linear distance of that slider joint. So for example, in the steering, we've got the shaft inside of essentially a rack and pinion. So this slider joint right here, if we take a look at it, so if we select it on the screen and we find it in the browser, you can see that it's all the way down here in the steering rack. So that slider joint, if I say drive joint, I can say, well, I want to see what happens when I move the steering 1 inch or when I move the steering 2 inches and see how much what the difference in toe or caster or camber is at a specific suspension travel point. So if you have something set up like that with a shock or a strut that has a slider joint, you can drive it in that way, which is going to be a much more accurate way to see what you have through your entire suspension travel. Keep in mind as well, the way that we set these designs up, you can always go back and move these components around and restructure your sketches and change the suspension geometry. Now, this one was sort of the next step after we did the initial suspension setup with just sketches and components without worrying about all these, solid sort of fake bodies for the steering wheel and this other stuff. So those were set up in a way that we really were looking at just the basic geometry points. And that's a really good sort of stopping point for you to figure out that suspension before you progress into building these 3D models. So you can always go back and and tweak those points and move them around and see how it progresses. But again, it's very much a brute force method. You have to measure everything out manually. So at this point, that's as far as I'm going to take this. If you have any questions, please let me know. As always, thanks for watching, and we'll see you in the next one.